Hello dear students. So this lecture will be on cross-spectral techniques. We have seen even detection in EEG signal using various methods like autocorrelation function. So here we will discuss mainly about the spectral techniques. So we have seen that the multiple peaks that arise in the autocorrelation function or cross-correlation function may cause confusion in the detection of rhythms. The analyst may be required to discount peaks that appear at integral multiples of the delay corresponding to a fundamental frequency. So the Fourier domain equivalent of autocorrelation function or the cross-correlation function permit easier and more intuitive analysis in the frequency domain than in the time domain. So the notion of rhythms would be easier to associate with frequencies than with corresponding inversely related periods. So now let's begin with the coherence analysis of EEG signals. So the problem here is to describe a frequency domain approach to study the presence of rhythms in multiple channels of an EEG signal. The Fourier domain equivalence of the autocorrelation function and the cross-correlation function are the power spectral density, that is generally represented as PSD, and the cross spectrum, that is cross spectral density, represented as CST respectively. So now let's study the presence of rhythms in multiple channels of an EEG signal, and we'll see the frequency domain approach. So as I mentioned that the Fourier domain equivalent of the autocorrelation function ACF, that is PSD, power spectral density, it is given as you can see in this equation, capital S XXF, that is a representation of power spectral density. F here represents that it is in frequency domain. So that is the Fourier transform of autocorrelation function of XX, and it is given as the multiplication or the product of Fourier transform of the signal itself with the conjugate of the Fourier transform of again the same signal. So it will result into mod of XF square. Similarly, we can find the cross spectral density, that is because it is a frequency domain equivalent of cross correlation function. So you can see here we are showing XY. So that is represented as theta, means Fourier transform of this cross correlation function. So it will be the product of the Fourier transform of one signal with the conjugate of the Fourier transform of the other signal. The power spectral density displays peaks at frequencies corresponding to periodic activities in the signal. This property facilitates the detection of rhythms in EEG signal. Mainly, the presence of alpha rhythm is indicated by a peak or multiple peaks in the neighborhood of around, either you can say 7 to 12, in some books it is 7 to 12 Hertz, or in some it is 8 to 13 Hertz. The power spectral density may also be studied to locate the presence of activity spread over a specific band of frequencies, such as the formants in the speech signal. And the cross spectral density, it displays peaks at frequencies that are present in both the signals being compared. And it may be used to detect rhythms present in common between two channels of the EEG signal. And one more parameter we can assume, that is the normalized coherence spectrum of the two signals. So that can be computed using the cross correlation and autocorrelation, means I can say the power spectral density and the cross spectral densities, as you can see. So it is given as whole under root mod of S xyf square, that is the cross spectral density square, divided by the product of power spectral densities of the individual signals. And the phase of coherent spectrum is given as we can see this equation, that is the phase of mainly the cross spectral density. This represents the average phase difference between the common frequency components in two signals. Now let's see different examples. The coherence between the EEG signals recorded from different positions on the scalp depends upon the structural connectivity or functional coupling between the corresponding parts of the brain. Investigations into the neurophysiology of seizure discharges and behavior attributable to disorganization of cerebral function may be facilitated by coherence analysis. The symmetry or lack thereof between two EEG channels on the left and right sides of the same position may be analyzed via the cross-spectral density or the coherence functions. Now you can see these two figures. Figure A and B both illustrates the power spectral densities of EEG segments with and without the alpha rhythm. The first one shows a strong and clear peak of means you can say around 9 Hz, this peak, indicating the presence of alpha rhythm. And if you see this figure B, there is no peak in the alpha range. So we can say there is an absence of alpha rhythm in the signal. Now let's discuss some examples. So this figure, if you see, it shows the EEG signal which we have taken for P4 from P4 channel, and it is displaying alpha rhythm. So we are taking this window, if you see, of 4.67 to 5.81 second, and we have obtained the autocorrelation function of this. You can see in time domain we have computed this autocorrelation function. So this displays peaks at time delay of 0.11 second and their integral multiple. So you have number of peaks. And if we compute the power spectral density, if you see, it indicates a strong and clear peak at about 9 Hz, indicating the presence of alpha rhythm. So the power spectral density displays a single peak through although the corresponding autocorrelation function has multiple peaks at 2, 3, and 4 times the delay corresponding to the fundamental period of the alpha wave in the signal. Now let's see one more illustration. Here we have taken two signals, two EEG signals. Basically these are from different channels. So we have considered P3 and P4 channels. And for this we have taken this window, if you see, 4.72 to 5.71 seconds, and we have computed the cross correlation function. So you can see it is showing peaks at the respective alpha rhythm locations, but that will be more clear if you compute this cross spectral density. So it shows a strong and clear peak at about 9 Hz, indicating the presence of alpha rhythm. So this single peak at 9 Hz in this cross-spectral density is more easily interpretable than the multiple peaks in the corresponding cross-correlation function. Now let's look at another example. These are the signals which we have obtained using channel C4 and O2, and we have taken this window. If you see, this is 5.71 to 6.78 second. So in this it is clear, we can see that in C4 there is no alpha rhythm, but in O2 the alpha rhythm is there. So if you compute the cross correlation function of the two, you'll get this kind of function. And if we compute the cross spectral density, So it lacks a clear peak in the alpha range. Even though the corresponding cross correlation function shows a peak at around, you can see at around 0.1 second, it is showing a kind of peak. So it is less significant than the previous, means what we have seen in P3 and P4. This is because in this case, one channel has alpha activity and the other does not have any alpha rhythm. Now let's look at one more example. We have taken now the signals from channel F3 and F4. So in this, both the channels are not having any alpha activity, and we have taken this window of 4.13 to 4.96 second. So you can see when we compute this cross correlation function, it is not showing any peak. And also if you compute the cross spectral density, it is very clear that it lacks the peak in the alpha range because the two segments have no alpha activity. So by this way, by using these spectral techniques, power spectral density and cross spectral density, we can detect these alpha rhythms present in the EEG signal. So for this topics, you can refer the book Rangaraj M. Rangayan, that is Biomedical Signal Analysis, a case study approach. So for now,